Well, welcome. My name is Masahiro Mori, and I hope some will stop making funny faces. I'm the current chair of the Department of Physics, and it is my honor and pleasure to welcome you to this year's David Lee Historical Lecture in Physics. But before we introduce our speaker for tonight, there's one important tradition business we would like to attend to, that is to present this year's Morris and Gertrude Goldhaber Prize. So, is this key? I hope. Okay. All right. For some of you who have not heard of their work, Gertrude and Morris Goldhaber were, well, what do you think? Physicists. It may not come as too much of a surprise. Who did really pioneering research in nuclear physics in the sort of early to mid 20th century, and I believe they were born in 1911. Morris was born in Austria, and Gertrude was born in Germany, and they started working together in the mid 1930s at Cambridge University. Then they moved to University of Illinois. Morris moved in 1938, and Gertrude moved in 1939. And there, they did many very interesting experiments in nuclear physics in the 1940s. And one of the experiments that are rather well known is, for example, the experiment in which they studied beta decays of radioactive nuclei and showed that what people usually said beta ray is in fact exactly electrons. You know, the kind of thing that you see in textbook and you don't wonder about it, and those things have been found there. And around 1950, they moved to Brookhaven National Laboratory in Long Island. The lab was relatively recently built. I believe the lab was built in 1947, and they immediately started working on research in particle physics. Well, they probably called it nuclear physics those days. We recognize that as particle physics. And among many, many experiments and exciting discoveries they've done, the most famous one probably is the experiment in which Morris showed definitively that helicity of the neutrinos was always left-handed. And that's the PhysRev paper in 1958. And Morris went on to become a lab director at Brookhaven from 1961 to 1973. And they lived very long, productive lives until very recently. So tonight we're fortunate to have Morris and Gertrude's son, Professor Fred Goldhaber. If you could just raise your hand so that people could recognize you. Thank you very much for coming. And to celebrate the legacy of Morris and Gertrude, we give Goldhaber Prize to the brightest graduate students in our department each year. So each year we pick among the graduate students who passed the qualifier exam during the last academic year and select one or two really good experimental physicists, one or two really good theoretical physicists. This year, we are giving prizes for 4 of those brilliant young physicists. And they are, okay, let's start from Dennis. Dennis Wang. Dennis, please come. If you don't stand up, nobody can. He's an experimental physicist working with Jenny Hoffman. Congratulations. Next, Shu-Hen Shao. Shu-Hen. He's a theoretical physicist working with Jin. Thank you. And third up, Beaulieu, another theoretical physicist working with Rick Heller. And the last one is, there you go. How do I close this one? Okay. Yes, I can see you. There. Okay. So that's Sion-san, experimental physicist, and unfortunately he's too far away to get the check. You will get it. Okay, believe me, you will. I'll give it to Melissa. Okay, he's far away because he's in Geneva working at CERN on the ATLAS experiment at the Large Hadron Collider. So say something. We can hear you. We can hear you.
I don't know. I was about to say something. I'm very happy.
Okay.
I'm happy that Melissa and so many of the graduate students and the professors who I work with have such faith in me. I think that, I don't know how it is in theory and maybe other parts of physics, but at least in particle physics, there's actually very little that really, you're the only one that can do it. And in order to be successful, other people must believe in you and think that, that you can do something, and they will give you the job over giving it to someone else. And I'm just very thankful for all the opportunity and the faith that my advisor, Melissa, has had in me these several years, and all the opportunity that she has given me. So.
Wonderful. Thank you, Sam, for calling in. Okay, now, yes, I can disconnect you. Thank you. Okay, let me now turn the podium to the professor and the commentator.
Okay, so it's my pleasure and honor to introduce Steve Weinberg tonight, who's the Jose Riesenthal Professor at the University of Texas in Austin. Steve is the recipient of many prizes, the Nobel Prize, the National Medal of Science, the Franklin Medal. More interestingly, he's an old friend here at Harvard, and it's really great to welcome him back here. Steve played a central role in our modern understanding of quantum field theory. And quantum field theory is one of the crowning achievements of science in the 20th century. It's a theory which has been tested to historically unprecedented accuracy, 14 decimal places, some of that here at Harvard. And the final form of what's called the standard model of quantum field theory was written down by Weinberg in 1967. And within a decade, experiments had revealed almost beyond any shadow of a doubt that this theory was correct. And he was honored with the Nobel Prize, along with Glashow and Salam, and then proceeded to immediately leave Harvard. I don't know why. And, but even though it was, Nobel Prize came in the 70s, the final piece of the standard model took 45 years to put into place. And the final piece of that, the Higgs boson, was discovered only several years ago, finally verifying the 1967 work in its entirety. And Steve is now writing a book on the history of science, and I don't know so much about it, but in my impression, it's pretty rare to write down some equations and have people spend 45 years and billions of dollars trying to verify them and then have it turn out to be correct down to the last detail. Now, in addition to the Standard Model, Steve has had many important contributions to physics over the last half a century. Those include the soft theorems that he discovered in the early 60s, which have controlled everything that we study about infrared phenomena at accelerators, and also are affecting modern developments in string theory. In the 70s and 80s, he shaped our understanding of quantum field theory as an effective field theory, not a fundamental field theory. And also I would, though maybe this one isn't always mentioned, I would mention his 1988 prediction using anthropic arguments of a cosmological constant, which was subsequently experimentally verified within an order of magnitude to be correct. And unlike his other predictions, this was an extremely annoying prediction because all good physicists dislike the anthropic principle. But the correctness of this prediction has forced all of us to rethink that, or the verification of this prediction has forced all of us to rethink it and change some of our views about how the universe around us works. Now, in addition to being a great physicist, Professor Weinberg is also a great communicator and an inspiration to many. He has written a number of very influential and successful popular books. The First 3 Minutes, Dreams of a Final Theory, which I'm now teaching to my freshman seminar class. And he's also a great teacher. I myself, as an undergraduate, took Physics 210 from him, a course which, General Relativity, taught from his book, a course which I now myself teach at Harvard. So he was personally very inspirational to me, and thank you for that, Steve. And so now I'll turn the podium over to Professor Weinberg.
I am mic'd up. Oh, you are mic'd up. Yeah. Thank you, Andy. Well, thank you, Andy, for those kind words. I wish I could say I remembered you in Physics 210. I don't remember teaching Physics 210. This is the first I've heard of it. Anyway, I'm very glad to be here to give the Lee Historical Lecture and grateful to Andy for inviting me. I'm also glad that this is associated with an award to 4 students in the name of Gertrude and Morris Goldhaber, who were dear friends of my wife and myself. It was nice just seeing their pictures on the screen. That was an unexpected pleasure. I'm also grateful to Andy for inviting me to attend his class this afternoon, which all I can say is it's nice to see Harvard still gets some pretty good students. Now, I think I'll start by invoking the spirit of Isaac Newton. Always a good start. Newton, in 1704, wrote a book, The Optics, in which he described his theories of light, and in particular of color, and the experiments that he had done on them. I'm not going to be talking about that. In The Optics, he took the occasion to look into the future and try to see some of the shape of future physical research. He knew very well that in his great work a quarter century earlier, the mathematical principles of natural philosophy, where he had laid out the theory of gravity and the theory of motion, and for the first time really dynamically understood the solar system, he knew that he had not succeeded in solving the problems of physics, that in particular, the nature of matter and what gave matter the properties it has was completely not understood at the time. And so he looked forward to what kind of theory would explain the properties of matter. And he knew it was not just gravity. Also, it was not gravity together with magnetism and electricity, which were known since antiquity, but that something else was needed, some other forces of short range that would act only within the particles of which matter was composed. Here is what he said. I don't know if you can read this, but I'm going to read it to you. The attractions of gravity, magnetism, and electricity reach to very sensible distances. They're long-range forces. And so have been observed by vulgar eyes, people in general. And there may be other forces which reach to so small distances as to escape observation. In other words, there are forces that determine the properties of matter, but which we don't know about from vulgar observation because the range is so short. This turned out to be true. At the turn of the 20th century, it was discovered that matter, well, it wasn't discovered, it was already suspected for a long time, but it was confirmed at the beginning of the 20th century that matter does consist of atoms. Atoms themselves are mostly held together by the electric force. But then in 1911, in Rutherford's laboratory in Manchester, it was realized that most of the mass of the atom, most of the mass that makes up us, is contained in a tiny nucleus around which the electrons revolve like planets around the sun, held in their orbits by electric forces, but that the nucleus itself would have to be held together by some kind of other forces, which, as Newton anticipated, were of very short range. These forces that hold the nucleus together came to be known as strong nuclear forces. Also, every once in a while, a nucleus suffers a cataclysmic change into a nucleus of a different element, emitting an electron. This is what Maurice Goldhaber worked on. And this change of the nature of the nucleus, which Rutherford understood explained radioactivity, had to be due to some other kind of force which can change nuclear particles of one type into nuclear particles of another type, which came to be known as the weak nuclear force. It doesn't hold anything together, but it acts, like the strong nuclear force, it's short range. It acts only inside the atomic nucleus, and it allows nuclei to change their nature, emitting electrons and neutrinos. The challenge was to understand these forces, and that challenge was met largely in the 1960s and the 1970s. And by the 1970s, we had a perfected theory, the standard model of strong, weak, and electromagnetic forces, which accounts for everything we observe in our, I should be a little bit more modest, which is consistent with everything we observe in our laboratories in the behavior of elementary particles. A good deal of the work of putting together this standard model was done here in the greater Cambridge area. And in particular, at Harvard, where I was in the 1970s, there was a brilliant galaxy of stars of theoretical physics, who I mentioned in alphabetical order: Appelquist, Coleman, Georgi, Glashow, Politzer, Quinn, Witten, and me, I'm proud to say. Now, Newton anticipating the existence of structures at forces that would only reach to very short distances, and hence a new world of physics that was only accessible when we could study very tiny scales, had no idea how tiny that scale had to be. He anticipated that there was some very tiny range forces which were needed to explain matter, but he didn't know what that size would be. Today we know that Newton was a long way away from it. That is, his scale, let's say the height of Isaac Newton himself, was 10 to the 15, that's a million billion, times larger than the size of the radius of a typical nucleus. And so he had a 15 orders of magnitude to look forward to exploring before he could get to his short-range forces. He didn't know that, of course. We today, like Isaac Newton, are in a position to say, yes, there must be scales of distance, whether it's the range of a force or the Compton wavelength of a particle, whatever. There are scales of distance which play a role in physics at a very fundamental level, which we have only bare clues to, but we have the advantage over Newton that we can anticipate the scale at which this new physics will be found. And that's what I mean by glimpses of a hidden world. We have 3 glimpses. I mean, by 3, I don't just mean speculation, but actual experimental evidence that, although it doesn't reveal what is going on in this hidden world, at least strongly suggests that it exists and what its scale is. The 3 clues, which I'll be talking about, are the convergence of the intrinsic strengths of the various interactions of the Standard Model, the weakness of gravitation, and the masses of neutrinos. And all 3 agree that the new scale of physics, which we have to reach, at least intellectually, in order to make real progress toward a fundamental theory, is of the order of magnitude compared to the nucleus of an atom, compared to the radius of a typical nucleus, about 17 orders of magnitude smaller. Smaller by a factor, that is, of 10 to the minus 17, and I've written down here what 10 to the minus 17 is. Possibly 10, even smaller, 10 to the minus 19, somewhere in that range. But when you're talking about 10 to the minus 17 or 10 to the minus 19, what's a couple of zeros? It's in that range that we expect to find really new physics. So let me take these in order. The first has to do with the convergence of the interaction strengths of the Standard Model. This really brings me back to the 1970s when I was at Harvard. I was sitting in the faculty room, the same room where I met with Andy Strominger's class this afternoon, and I was listening to a talk by a student of Sidney Coleman's, U. David Politzer. And he drew a curve. I've tried to, this is all freehand drawing, it's not to be taken literally, but he drew a curve something like the blue curve on the top of the figure. In this curve, the strength of interaction increases upward, distance decreases to the right. So as you go to the right, you're talking about smaller and smaller scales. The left-hand part of the picture shows the great discovery that Politzer and also Gross and Wilczek at Princeton had made, which was the breakthrough that led to our understanding of the strong nuclear forces, that The strong nuclear forces are very strong at large distances. That is not the force between neutrons and protons, which are not really elementary, but the forces between the quarks of which neutrons and protons are made are extremely strong if you try to pull them apart, which is why we can never see them in isolation. This was a great breakthrough because the idea of a quark was very attractive, but why weren't we seeing quarks? Well, this work explained it. But that as you go to shorter and shorter distances, the strong force becomes weaker and weaker. And that had been suggested by experiments on high-energy scattering, that if you probe an elementary particle like a neutron or a proton at very small scales within the neutron or proton, it looks like the quarks are not interacting very strongly with each other. This phenomenon of becoming weaker at decreasing distance is called asymptotic safety. Excuse me, asymptotic freedom. Asymptotic safety is something else. As I was sitting there listening to David Politzer and showing this curve, I suddenly thought of the other forces of the Standard Model, the weak and electromagnetic forces, which we lump together as electroweak forces. They have two independent characteristic strengths, that is, numbers that describe the strengths of the forces. And it was known that they vary slowly, one of them increasing a little bit, the other decreasing. The curves here are not to be taken seriously. And I imagined in my mind these curves near the bottom in the red and orange, the electroweak curves, and what would happen if you projected these curves all the way to the right, many, many orders of magnitude in distance to the right. And the same thought must have occurred at the same time, although I never quite discussed with them how they came to it. But the same thought must have occurred to Howard Georgi and to Helen Quinn, because the three of us got together in a collaboration where we calculated what these curves would do. And by God, they all three came together at an energy which was, well, at a distance which was like the distance that I was referring to, about 10 to the minus 17, a 10 million billionth of a nuclear radius. This was extremely exciting because, you know, a lot of the payoff we were seeking was unification. Theory, we had already achieved a kind of unification of the weak and the electromagnetic forces. Then there were the strong forces, which were obviously much stronger. A number of brave theorists, particularly Patti and Salam in 73 and Georgi and Glashow, later but in a more attractive theory in 1974, had speculated about some kind of union of all the forces of the Standard Model, strong, weak, and electromagnetic. But they faced the obvious problem. The strong forces are stronger than the others, so how can they be unified? They're very much stronger, especially if you go to large distances. And this now was a suggestion that, in fact, although it didn't particularly tell us that either Patti and Salam or Georgi and Glashow were right, it did strongly support the idea of a theory that would combine the strong, weak, and electromagnetic forces where the apparent differences between them arose from a breakdown of some kind of symmetry, and the breakdown was associated with some other forces whose range was about 10 to the minus 17 nuclear radii, and what seemed like almost an absurdly small distance. Well, why don't we just do experiments, probe those small distances and see what's going on? It's not so easy. If you want, for example, to have a photon with a wavelength like this, its energy would have to be about 10 to the 16 GeV. That's 10 million billion GeV. A GeV is the energy contained in the mass of a proton. Or in other words, 10 trillion times the highest energy that we can reach now. You know, if somehow physicists convinced the world as a whole that all the economic resources of the human race should be devoted to this, we would not have any idea how to reach such energies. So in the famous words of Tony Soprano, forget about it. The second, that is, forget about a direct experimental exploration of these scales. I'm afraid we must forget that for the foreseeable future. This kind of a distance, 10 to the minus 17 nuclear radii, was not entirely unfamiliar to us. And it rang a bell because we had seen it before in a different context, having to do with the extreme weakness of the force of gravity. You can suppose you want to consider between two protons or two electrons, there is an electrical repulsion. Suppose you ask how heavy would they have to be for the gravitational attraction to balance their electrical repulsion. It doesn't, of course, in the real world. In the real world, we never see effects of gravity within the atom. Gravity can be totally ignored when you study the mechanism of atomic physics, but how heavy would the proton or the neutron have to be in order for their gravitational attraction to balance their electrical repulsion? Well, the energy would be not 10 to the 16 GeV, which was what I mentioned earlier. That's the energy of a photon with a wavelength of the scale I was talking about where the couplings come together, but a little bit higher, 2 orders of magnitude higher, but still in the same general ballpark. This energy we can calculate precisely. It's 1.04 times 10 to the 18 GeV. It's known as the Planck energy. It actually was first brought into physics not in connection with quantum mechanics, but by Stoney. I think it's George Johnstone Stoney, I'm not sure, in 1881, based on the estimates which were then current of the charge, of the fundamental unit of charge. It wasn't known to be the charge of the electron, but it was believed that there was a fundamental unit of charge that was transferred, for instance, in electrolysis. And Stoney actually calculated this number called the Planck energy, not as accurately as I'm giving it here. So there is a strong suggestion that gravity is somehow unified with the other forces at these small scales. In fact, I remember that Georgie and Quinn and I were relieved that the scale we had found where the couplings came together was somewhat lower in energy or larger in distance than the scale of the Planck scale, because it meant that our calculations, which ignored gravity, were not thereby wrong. I mean, that, in fact, it was legitimate for us to ignore gravity, although not by much. Now, the last clue to the existence of a hidden world is the mass of the neutrino. But in order to explain this, I first have to provide a brief digression on fundamental constants. When you have a theory that contains a fundamental constant, it relates different scales which otherwise would be independent. For instance, the speed of light relates the scales of energy and mass because of Einstein's relation, E equals mc squared. A certain amount of mass is equivalent to a certain amount of energy, and you find out what that is by multiplying by the square of the speed of light. Not an unfamiliar fact. And even more obviously, it relates distance and time. The distance light travels in a certain time is the speed of light times the time. In the same way, Planck's constant, h, together with the speed of light, relates energy and distance. I've already mentioned that there's a relation between energy and wavelength. The energy of a photon with a definite wavelength lambda is Planck's constant times the speed of light divided by lambda. Now, theorists today, I'm afraid it may be a bad habit, but we all have it. We often use natural units where the speed of light is 1 and a reduced version of Planck's constant h over 2 pi is 1. So in other words, energy is equivalent to mass, which is equivalent to the reciprocal of distance, and is equivalent to the reciprocal of time. For example, the electron mass, if you converted the electron mass into energy and gave that energy to a photon, the wavelength of that photon would be 3.86 times 10 to the minus 11 centimeters. And if you had 10 times the mass, then the photon wavelength would be 10 times shorter. Now, in the Standard Model, as in the earlier theories of Maxwell and Dirac, all the field equations are simple. And in particular, in natural units, which I've just described, there are no constants appearing whose units are length or length square or any positive powers of length. And this imposes, well, this is a way of describing the simplicity of the equations, because it limits the number of powers of fields or rates of change appearing in the equations. Now, generally speaking, physicists from Einstein, certainly Maxwell, Dirac, physicists in general, when they're trying to understand a new phenomena, assume the equations are as simple as possible, as simple as consistent with known principles and with known data. That's a good strategy for physicists. First, try something you can work with easily before mucking it up with complications. But even if you're successful, as Einstein and Maxwell and Dirac and others were, and as we were, and we did the same thing in the Standard Model. We took the equations to be as simple as possible. Even when you're successful, you have a responsibility after the fact to explain where that simplicity came from. Just to say that God prefers simple equations somehow isn't entirely satisfying, although some people have perhaps felt it was. Now, starting in the late 1940s, in the context of electromagnetism, we thought we had an answer to the question. The equations of electromagnetism are very simple, and in particular, there are no quantities, there are no coefficients of the various terms in the field equations which have the units of length or power or length square or any positive power of length. If we allowed such terms, the theory could be arbitrarily complicated, but we don't allow such terms. We impose simplicity. Now, starting in the 1940s, we thought we had a reason for that, and it had to do with the appearance of infinities. Infinities in simple theories, theories which satisfy this criterion about the units of the constants in the theory, can be canceled by a proper definition or renormalization of constants like physical charges, physical masses, and so on. And such theories, this is called renormalization, and such theories are called renormalizable. But in other theories, where there are constants with the units of length, always in natural units, where h bar and c are 1, where there are constants with the dimensions of length to some positive power, when we sum over the wavelengths of photons or other particles in intermediate states, we usually encounter contributions that become infinite when we allow the wavelength of the particles to be arbitrarily small. If we cut off the sum over intermediate wavelengths at a certain minimum wavelength, say we simply won't consider any wavelength less than that minimum, we find we get contributions whose constants are powers of length divided by those powers of the minimum wavelength, so that when the minimum wavelength is allowed to go to 0, these infinities blow up. And it appeared that these infinities are not of the kind that can be canceled by renormalization. This was a problem for early theories like Fermi's theory of the weak interactions. In natural units, the constant that governs the strength of the weak interactions has the units of length square. And this was a great bone in our throat until these theories were replaced by the renormalizable electroweak theory, which doesn't have any constants whose dimensions are positive powers of length. But there are other successful field theories that obey symmetries that require there to be terms in the field equations that are proportional to constants that in natural units are positive powers of a length. And among these theories are gravity itself, the constant of gravity, Newton's constant, although he never had it in the Principia, but we call it Newton's constant, has the units of length square. And that means that Einstein's theory of general relativity is not renormalizable. The infinities can't be eliminated by being absorbed into constants. And also a theory of low-energy pi mesons, which I worked extensively on in the early 60s, also does not allow any renormalizable theory. The basic constant in this theory has, like Einstein's constant, the dimensions of length square. So what do you do? Well, I think there is a different modern viewpoint which has gradually matured over recent years. By the way, I should say that I was happy to give Loeb lectures here on this theory of low-energy pions and ideas of gravitation in the early 90s, in 92, 93. And then I presented what I regard as a modern viewpoint in my Loeb lectures in 95, 96. The modern viewpoint is that all terms in the field equations that are consistent with symmetry principles like Lorentz invariance or gauge invariance do appear in the field equations. If it's allowed, it's compulsory. But the lengths that appear as coefficients of these complicated terms, which destroy the simplicity of the theory, are very small. In such theories where all possible interactions appear, all infinities are absorbed in a redefinition of the constants in the field equations. And in fact, the slogan that I provided in my Loeb lectures was that non-renormalizable theories are just as renormalizable as renormalizable theories. Take that. Now, I'm coming back to neutrino masses eventually. If you allow a theory like the Standard Model to contain arbitrarily complicated terms simply suppressed by higher and higher powers of some very small length, then any symmetry of the Standard Model that's a mere accident, that's there only because the equations of the Standard Model are too simple to violate it, any such symmetry is bound to be violated, but by very small effects, because we're talking about very small lengths. One of these, and Wilczek and Z and I both adopted this viewpoint and cataloged some of the new kinds of effects that could be produced by higher terms in the field equations that are suppressed by small lengths. One of them was proton decay. The field equations with these higher terms in it contain terms that allow 3 quarks to turn into an electron or a neutrino with a rate proportional to some new length to the 4th power. And that length doesn't have to be very small for proton decay to be unobservable, although I think there still is a good prospect that eventually we will see proton decay produced by such terms. Neutrino masses are different in the sense that we have observed them. The interaction energy, according to the modern viewpoint, must contain terms that are allowed by the symmetries of the Standard Model. These terms involve a pair of electron and neutrino fields, a pair of Higgs fields, and a constant with the units of length, not length to the 4, but just 1 power of length. We now know that the Higgs fields, well, in fact, we've known since 1967, that the Higgs fields have a vacuum expectation value of 247 GeV. And if we assume that there are no very large or very small dimensionless constants in this interaction, then the fact that we observe neutrino masses in the general neighborhood of 0.01 volts tells us that this length is, well, the reciprocal of the length is 10 to the 15 GeV. In other words, the length is like 10 to the minus 16 times the size of an atomic nucleus, in the same ballpark. And of course, this is very crude because we don't yet know the neutrino masses in detail. We don't know the theory here that this interaction may contain constants that are a tenth or a hundredth or 10. So this is a very crude estimate. But the masses of the neutrinos which are being observed are in the same ballpark that you would expect from new physics associated with a fundamental length, like the length at which the couplings, the interaction strengths of the standard model come together, and the length converted into an energy at which particles attract each other gravitationally as much as they repel each other electrically. It all seems to hang together. Now, oh, by the way, I should say these effects of proton decay were seen earlier in models of Georgi and Glashow, and neutrino masses in models of Gell-Mann, Raymond, and Slansky. But the point that Wilczek and Z and I were trying to make, if I can guess what their way of thinking was, is that these are endemic. This is what you expect in any theory, because the symmetries that keep protons stable and keep neutrino massless in the standard model are just accidents. They're just accidents of the simplicity of the theory. And as soon as you allow the theory to contain more complicated terms, as I think you must, then these symmetries are violated and protons can decay and neutrinos get masses. Likewise, there's no reason to suppose that Einstein's equation for gravitational fields are as simple as he thought. Terms involving constants with extra powers of length must appear in astronomical calculations divided by powers of the very large lengths of astronomy, and therefore they're undetectable. They're undetectable in ordinary astronomy. They may play a very important role in black hole collapse or in the very early universe. You know, there are theorems that say once a certain stage has been reached in the collapse of a black hole, the further collapse is inevitable. I don't think those theorems are right because they are proved within the context of ordinary general relativity. I think that all you can say is that once certain conditions have been reached in a black hole, the black hole collapse will continue until general relativity itself, in the simple form that Einstein proposed, breaks down. And you begin to be sensitive to the more complicated terms, which must be there in the field equations of general relativity. By the way, talking about things that we only know about because they violate symmetries, we only know about gravity because I should say, we can only observe gravity directly because we happen to live on a sphere containing about 10 to the 51 protons and neutrons, all of which are pulling at us. And if it weren't for that we happen to live on such a large mass, we would never be able to detect gravity in the laboratory. Look, every proton and neutron of these 10 to the 51 is attracting this bottle of water to the center of the Earth. And yet I, with my feeble muscles, can hold it up, purely electrical forces, and, I win. But it's only because I can do that because gravity is so incredibly weak. And in fact, I'm going to take the... I deserve that. So now the big question that we face, I'm out of time, so I have to get to it, is that can we find a truly fundamental theory uniting all the forces, including gravitation, whose structures are characterized by tiny lengths like 10 to the minus 17 to 10 to the minus 19 nuclear radii? Is it a string theory? We don't have, I mean, that seems like the most beautiful candidate, but we don't have any direct evidence that it is a string theory. The only handle we have, aside from things I've mentioned, like the neutrino mass, possible proton decay, the weakness of gravity, and the convergence of the couplings, the only handle we have on this to do further experiments is in cosmology. Because in the very early universe, in the period of inflation, the energies may very well have been as high as this energy of 10 to the 18 GeV per particle. There are actually experiments that can tell this, because if the energy density in the very early universe is that large, then gravity, which couples to energy, would have gravitational radiation would have been strongly produced. In addition to the purely scalar waves of pressure, like sound waves, that resulted in the large-scale structure we see, galaxies and cluster of galaxies, the very early universe, the period of inflation, would have generated gravitational waves which could leave their imprint on the microwave background, which is ordinary electromagnetic radiation, but is affected by the charged particles when the universe was 380,000 years old, which in turn were affected by could have been attracted by gravitational waves. There is an experiment called BICEP-2, which indicates the discovery of just such gravitational waves. And it does suggest that the density of energy in the early universe during the period of inflation was characterized by this scale of the order of 10 to the 18 GeV or 10 to the minus whatever it is, I've forgotten now, nuclear radii, 15, 16. This experiment is not definitive. There's a big question hanging over it whether or not the effects they are seeing are produced by dust in the relatively recent universe, having nothing to do with the very early universe or with gravitational waves. And we simply don't know. We're waiting to hear from observers, whether or not, and there are ways of distinguishing them, whether or not the BICEP-2 results really do represent gravitational waves from the early universe. But if they do, and I think there's a 50% chance, then it will be another piece of concrete evidence that there is something fundamental about the scale of 10 to the minus 15 nuclear radii at which we can expect a true unification of all the forces of nature. Thank you. I'm happy to answer questions, unless you ask what the theory is.
Thank you for your great lecture, and I'm really excited to be here attending your lecture. So my question is related to both science and history. So during the process of human civilization, human beings have been exploring the universe for so many years. And today, we have arrived such a mathematically consistent and also
Well, this is as I understand it, the question is, could different civilizations come to quite different understandings about nature? I think the answer is no. Not to try to pussyfoot about this. Clearly, the timing, the location of advances in physics depends on all kinds of societal effects. Robert Merton thought that the great blossoming of physics in England in the 17th century was due to the triumph of Protestantism. And he had arguments. I don't know whether that's true. But I do think I know why Newton's theory takes the form it does, and would take that form wherever it was discovered, and that's the way the world is. The world, to a good approximation, really does obey Newton's laws. Now, what evidence do I have for this? Obviously, there have been many civilizations which did not come to these conclusions. But modern physical science, which developed in Europe in the 16th and 17th centuries, has completely conquered the world as far as scientists who provide reliable knowledge on which you can base technology or government policy. In every country in the world, science is what developed in Europe in the 16th and 17th centuries, which in turn has roots among the Arabs and the medieval Europe, which in turn depended on the precocious science of the Greeks. But once we learned what the solar system was and what makes the planets go around the sun the way they do, we never will unlearn that, and no other society will ever replace that with a different picture. If I'm not, I don't know if I would bet my life on this, but in a sense I have bet my life on this. Because if in fact this is not true, what's the point?
Dr. Weinberg, I remember the first brown bag lunch that you had at UT shortly after Green and Schwartz had discovered the anomaly cancellation. And I think you described string theorists up to that point as being something like a psychiatrist. There was a new sense of optimism, however, at that time in physics, and a whole new world of algebraic topology and Calabi-Yau manifolds and all sorts of things opening up. Could you update us in a few words on where that state of optimism is at this?
Well, not really.
Today?
I did study string theory intensively in the 80s and gave a course on it and wrote a couple of really grossly unimportant articles whose function was just autodidactic. I was just writing articles in order to try to learn the subject. And then I saw it was getting very mathematical. You mentioned some of the things, Calabi-Yau manifolds and so on. And it was either do that and give up everything else I might do, or do other things like cosmology. And I chose the latter course. But not because I thought string theory was doomed. I think it still is the most attractive direction to go toward a truly unified theory. It has a kind of rigidity that I look for in a beautiful theory. That is, as I understand it, string theory becomes nonsense if you change it in little ways. And that's it. It is believed that there is one string theory, although there are many approximate solutions. Unfortunately, it has not pointed to a particular solution that looks like the real world, and string theory has had qualitative success, like requiring the existence of gravity. I mean, there's no string theory without gravity, because one of the modes of vibration of a string is the quantum of gravitational radiation. But it has had no quantitative successes, and it's the kind of theory that you'd like to believe in, but you have no firm ground for that. And I find it all very disappointing. I think, but that isn't to criticize the people who do it. I think because it's the most attractive direction to go, I'm very glad that there are people who immerse themselves in it. But I hope that experiments, either in cosmology or at very high energy, or in the quieter mode of looking for rare things like proton decay, I hope that experiments will give us a kick in the backside and get us moving in the right direction again, even though we don't have a good string theory. So I don't know what the future is going to bring. I think the fundamental principle of progress in physics is to keep working. And if your tastes are in string theory, that's a good direction to work on. If your tastes are in particle phenomenology, fine. If it's in cosmology, fine. That's very exciting right now. But I remember the tremendous excitement of elementary particle physics as I started out talking about in the 1960s and 1970s. You know, most Americans, if you say, what were the 1970s like, would say it was a period of inflation and unemployment. If you ask an elementary particle physicist what was the 1970s like, he would say it was great. We had experiments that were relevant to theory and theories that were relevant to experiment. It all was coming together, and all the problems of the standard model, like, for instance, the thing that Adler, Bell, and Jacques worked on, that pi zeros didn't decay the way they were supposed to. All that got settled in the 1970s. We understood it all. So it was a wonderful time. We don't have that kind of wonderful time in elementary particle physics these days. We do in cosmology, and maybe we will again in elementary particle physics. We'll see. Yeah. Yes?
So what about the cosmological constant?
I haven't even touched on that. That's, of course, an embarrassment. I said that you should allow every term in the field equations that is allowed by symmetry principles. And that includes terms with positive powers whose interaction strengths have positive powers of length. There are terms with negative powers of length, like masses, which of course have to appear in the field equations. But if you're really going to take that point of view consistently, then you should allow a term in the field equations that, like Einstein's cosmological constant, which corresponds to an energy density, hence goes like a -4th power of length. And if you take that length to be a tiny length, like the lengths we've been talking about today, or even perfectly normal astronomical lengths, like the size of the solar system, it gives an enormous energy density which would wreck the universe. I mean, it would cause the universe to expand so fast that galaxies and stars could never have formed. So there's about 122 order magnitude discrepancy between that estimate and the actual value that we observe of the dark energy, which is the modern way of looking at the cosmological constant. And nobody really has a good idea of why that one term is so incredibly small. The only idea that seems to work is something Andy referred to in his introduction of me, but is based on very wild speculation about multiverses, and certainly is not a firm enough success to justify those speculations, although those speculations may in fact turn out to be right on other grounds. So we don't know. I gave a series of lectures here at Harvard, I think in 1978, maybe 76, I'm not sure. I've given a number of Loeb lectures. And in that, I analyzed every theory that had been proposed for explaining why the cosmological constant or the dark energy was as small as it was. Many of them, by the way, predicted that it was 0, which of course now we know isn't true. And I found that none of them worked. I mean, they all had inconsistencies. In some of them, it wasn't so much that they were logically inconsistent as they simply amounted to saying, let it be very small. And the only one that seemed to work was this multiverse idea. But, of course, that's going way out on a limb, and I don't know if that's true.
One more question, and then...
Physics what? Principles.
I'm going to ask something about the physics principles. Like the some principles like the minimum functionals, or like the research on the different structure on manifold of the topological structure, like this kind of fundamental principles. So, what's your opinion? What is the most important or most basic principle in physics nowadays or in the future? I'm more interested in the future. Yeah, and actually, in the view, from the view of the theoretical physicists, that's my question. Thank you.
Well, the deepest principles I think we know are the principles of quantum mechanics. I personally find quantum mechanics unattractive in its present form. And there are various interpretations of quantum mechanics, all of which seem to me to have drawbacks. It would be a whole other lecture to explain that. So I think quantum mechanics will eventually be replaced by some other theory, but the trouble is that quantum mechanics has just that quality of beauty I referred to earlier, that if you change its equations in just a little bit, you get nonsense. And so I don't know what could possibly replace quantum mechanics. In addition to quantum mechanics itself, we have symmetry principles, and we don't know why nature obeys just the symmetry principles they do. But aside from quantum mechanics itself, those symmetry principles are the deepest things we know, and I suspect that will continue to be true. Well, thank you very much.